Okay, lesson 1.1 can change occur at an instant. Continued. More so again, it should be more introduction to calculus with the real life application. Problem number 2. A rock is dropped from the top of a 450-meter tower. What is the velocity of the rock 5 seconds after it was dropped? So this was a question maybe 600 years ago. I think his name was Galileo. He thought about this, maybe he was on top of a tower, and he let go of the leaning tower, Pisa. So you let go of a rock, and I think you have a good intuition on how the rock's gonna fall. At first, it goes down a little bit, but then because of acceleration, it starts going faster, and faster. So we say this is 1 second, and then 2 seconds, and then at 3 seconds, and at 4 seconds, and on. The difference in how much it has fallen is bigger than the previous second. You see that? This is bigger than this second, and then this. The difference between it, because it's picking up speed. The rate of change is different, and it's actually increasing. No, the velocity is. So how can we figure this out? It's like, so how do we do it? So let me give you, you can't actually do it if you don't have a formula for maybe, let's go back to what function f of t with respect to time, what function tells you at what height is the rock as time passes. So at least, can we come up with a function that tells you how high off the ground you are as time passes? And I will give you that function. This function is called s of t, which, don't get confused. It's not f of t, f, s, h of t could have been better, but we use s of t in calculus as a function for distances, so s of t is equal to negative 4.9 t squared plus 450 as the function that models the height of a rock with respect to time as it falls to the ground. So basically, if you guys have taken physics or will take physics, there's a acceleration, which is gravity. This is what tells you gravity. The height depends on gravity, and it also would depend on velocity. That's not here because velocity is 0. That's why it's not here in this function, because you just let it go. When you let go of it and you don't throw it, it has no velocity. In this last one is position. So it goes position, velocity, gravity. The position is that it's at the top of that leaning tower. I said 450 feet up in the air. All right, moving on. So now, can we graph this and figure out what it looks like on a graph? And again, if you remember from pre-calc, algebra 2, you should know that this is a quadratic function and it's upside down. So it should be some parabola going like this. You should already have an idea that it's an upside down parabola. Okay, let's graph it. So go ahead and you can pause the video and create your graph. And now we're gonna find at what height is that rock as time passes. Okay, so let's go ahead and do it. Height, time. So the formula is here. At time equal to 0, how high off the ground is it? We let go of it. At time equal to 0, it's 450 feet up in the air. So if you plug it into the formula, s of t is 0, and t is 0 squared. It's going to be 0 plus 450 is 450. Okay, so that's where you let go of the rock. And let's go ahead and do s of 1. So we're going to plug in t is 1 into the formula, into this formula. And then we get that as our answer. And as best we can graph it, go ahead and graph it. 1 and 445 could be somewhere right here. It's just an estimation of where it's at. So then we go S of 2 is that plug it into the equation and work it out. Calculator maybe good. So as we continue on, you verify these answers if you want. Get your calculators. So this is what we got. So it's upside down, okay? And you're like, where's the parabola? Well, the other side of the parabola would have been here or whatever, you know, but we don't need that. All right. So, okay, so we still haven't answered the question. What is the question actually? It says, what is the velocity of the rock 5 seconds after it was dropped? So in reality, what you need when it's talking about velocity, velocity means rate of change. And rate of change means, what does it mean? It's what we're trying to figure out. That's what we have been doing before. It's a slope. It's a slope for a curve. This is a curve. This is not a straight line. So we want to know what is the velocity at t equal to what? 5 seconds. So at 5 seconds, which is right here, what is the tangent line? It's basically what we had been doing, what we did in the previous problem. What is this slope of this tangent line? That's the question again. Everything else we do know. If even past just finding the velocity, if it says what is the equation of this tangent line, we have all the information. Y minus y1 equals slope x minus x1. We got the input is 5. The x1, that's going to be 5. And the output, whatever that is, which is at 327, right here, this is 327.5, is our y1. But what we need again is the slope, which is the slope of this tangent line. That's the problem. Okay, so how do we do that? Well, we're gonna do the table and find approximations. All right. Okay, so let's go to finding the approximation of the tangent line here. All right. And the way we're gonna do it is that we're gonna go to the next point and get this point, get closer. This is gonna become stationary point, and we're gonna get this closer and closer and closer to this point, so we can find that tangent line approximation. All right, so let's do our first approximation, and our time interval will be, I guess if these are the points I'm choosing, this is going to be stationary, so we're going to use this formula again, where the one that will actually be this is stationary. A will always be 5, and this would be, the B is the one that's going to be closer and closer and closer to it. So let's do it where A is going to be 5 and B is 6. Is that what I got? Yes. So this is A is 5, B is 6, and we're just using this m secant and doing exactly what we did in that other problem previous. So m secant is going to be 6 minus 5, and then we had f of 6 minus f of 5. You should already have all this information. What's f of 6? What's f of 5? 6 minus 5 is 1. Look at your notes. We should already have the information. Actually, it wasn't f. What was it? It was s. S of 6 minus s of 5 over 1. And that's going to be m secant for this first approximation. So the velocity here is about negative 53.9, which is a very good approximation, but it's not exact. Continue. Why don't we get this point closer and closer to the stationary point? Let's use 5 and 5.1, like really close. really close to each other, and then that's going to be closer to the tangent line. And you plug it into the formula, we're getting negative 49.5. We get it closer again, these are closer approximations. Negative 49.2, and you see that it's approaching, I think, negative 49. If we get closer, negative 49.049. If we do 5 and 5.001, it's negative 49.001. And if you really want to test it, we can go ahead and do 5 and 5.000001, and that one most probably definitely just give you that answer is negative 49. You can go ahead and put it in a calculator if you really want to, and we'll just say that the slope, the rate of change at this point is negative 49. And to answer the question, the actual question is, what's the velocity of the rock after 5 seconds? It's the rock is falling at a rate of 49. What is that, meters? Was that in meters? Let me go back. So meters, meters per second. And negative because it's going down. And that would be it for this part of the lesson.